Welcome you all for today's session, Introduction, that is Unit 1. So today we will be discussing Session 10 of Unit 1 of the course Design and Analysis of Algorithms. So the Unit 1 course outcome is discuss the fundamentals of algorithm. So the contents what we had learnt in introduction was what is an algorithm, fundamentals of algorithmic problem solving, important problem types, and at last it was fundamental data structures. So in fundamental data structures we have already presented with linear data structures, that is arrays and linked list. Linear data structures again two, that is stacks and queues. And in session 9 we had discussed graphs. And in 10 today we will be discussing trees, sets and dictionaries. Before we start our presentation on session 10, so just we will have a recap of session 7, 8 and 9. So in session 7 we had defined data structures, the different types of data structures, that are linear and non-linear data structures which are non-primitive. And again in linear data structures we had discussed arrays and linked list in session 7. In session 8 we had discussed stacks and queues. Stack is a structure which operates in LIFO fashion, which has push and pop operations, and queue operates in first in first out fashion, which has insertion and deletion operation. Then in session 9 we have discussed graphs. So in graphs we had known with the directed and undirected graphs, graph representation, that is adjacency matrix representation and adjacency list representation. And we had also discussed weighted graph and connected and unconnected graphs. We had defined what are paths and length for a graph and cyclic and acyclic nature of a graph. So today we will be discussing the session 10 of introduction, that is trees. So what is a tree? Tree, or else we can also call it as a free tree, which is a connected acyclic graph. Tree is also a graph which is acyclic, connected. So it is connected acyclic graph. We can term it as a tree. The number of edges in a tree is always one less than the number of vertices. So here it is represented as E is equal to V minus 1. If you take on with the magnitude. So then the tree is been given in the slide. So wherein the tree having the vertices A, B, C, D, G and F. So totally there are 6 vertices. So in the tree what you can see here, there is a all edges connected, all vertices connected, and there is no cycle in a graph. So we call it as a tree. So tree is a connected acyclic graph. So coming on with the further discussion. So a graph that has no cycles but not necessarily connected is called a forest. It may not have a cycle but still it is not connected, and that thing will form a forest. So in the picture here in this slide you can see there are two unconnected graphs. They are acyclic however, but they are not connected. So each of its connected components is termed as subtree. Okay, so each of its connected component is a tree. Then we will discuss what is a rooted trees. Rooted trees are defined with the first vertex as a root. So for every two vertices in a tree, any tree you take, for any two vertices in a tree, if there exists exactly one simple path, if there exists a simple path between those two vertices, that property makes it possible for choosing any arbitrary vertex in a free tree. So if you choose any arbitrary vertex in it, so it will have its name as a root and it will be called on as a rooted tree. So if for every vertices there, if for any if there exists a simple path between any two vertices, so of a tree, and if you choose arbitrarily any single vertex as a root, then that tree will be termed as a rooted tree. So rooted tree is formed for a simple tree, for a simple graph like this way. So there is a free tree in a picture at the left hand side, and the transformation of that free tree into a rooted tree, you can see choosing an arbitrary A as a root. You are choosing the vertex A as a root arbitrarily. Okay. So a rooted tree is usually depicted by placing its root on the top. Rooted tree it will be having its root on the top, that is at the level 0 of a tree. The vertices adjacent to the root below it will be at level 1. So the adjacent vertices for the root will be at level 1. The vertices 2 edges apart from the root will be at level 2, will be as shown below. Okay, so in your figure, the transformation, just see on the right picture. So A is chosen arbitrarily as a root, then B, so it will be at level 0. B, D, E are the vertices at level 1. C, G, F will be the vertices at level 2, and H and I will be at level 0, 1, 2, 3, third level. Okay, so you have to just know that in a tree, in a simple free tree, if you choose arbitrarily any of the vertices, you can easily form it with the rooted tree, having chosen that vertex as a root. Now we will define few terminologies concerned with the free tree. So if UV is the edge of simple path from root vertex, if you choose a edge UV starting from U vertex to V, so U is said to be the parent of V and V is called as a child. If you choose any of the edge of a simple path from root vertex U, from root vertex, sorry, it is not U as per. So if you choose any path, simple path, okay, from a root vertex, and there exists an edge UV, and then that time U will be the parent of V. Okay, so U will be the parent of V and V will be called as a child of U. So vertices that have same parent, so vertices which gets emerged from the same node or a vertex will be termed as a siblings. So vertices which have same parent are said to be siblings. So first one was child, and then the parent, and then the siblings, and now we will define the term leaf. So a vertex with no childrens are called leaf. Okay, a vertex which will not be having any childrens, child vertices, so then that vertex will be termed as a leaf. The vertex with at least one child, so if vertex has at least one child, that vertex will be termed as parental. The vertices for which a vertex V is an ancestor, so the vertices for which V is an ancestor, they are said to be descendants of V. Okay, so the vertices for which a vertex V is an ancestor, V will be termed as an ancestor. So the other vertices across that ancestor will be termed as descendants of V. V is an ancestor and the vertices of it will be termed as what? Descendants of V. All the descendants of V, vertex V, with all edges connecting them, all the descendants of vertex V, if you take V as a particular ancestor So if you take all descendants of vertex B with all edges connecting them, form the subtree for a tree. So wherein V will be the root. Okay. Now for the tree in the figure shown, you can see we will be defining a child, parent, leaf, siblings, descendants, ancestor and all. So in the figure you just concentrate on the right hand side. So the root here for this tree is A, vertex A. Then the vertices D, G, F, H and I are leaves. So who are all the leaves is H, I, G, D and F, because they don't have further childrens. So they are termed as leaves. Okay. D and then G, then F, H and I are all leaves. Okay. They are not having further childrens. So the vertices A, B, E and C are parental. They have at least one child. So they are termed as parental. A was having 3 childs, that is B, D, E, and B is having 2, that is C and G, and then E is having 1, that is F, and C is having again 2 child, that is H and I. So they are parental. A parent of B is A. Yeah, the parent of vertex B is A. And the children of B and C, the children of B are C and G. The children of B are who? C, vertex C and vertex G. Siblings of B are, siblings means who share or who have the same parent. So siblings of B are D and E. So B, D, E are all having a parent A as a parent will be for who? The vertex A. So the vertices of subtree rooted at B are, the vertices of subtree rooted at B are. So you can, if you want to have a B as a rooted tree, as an ancestor, so who are all the descendants of those, all the vertices which comes under it? So that is C, G, and again C is having 2 more children, that is H and I, which forms a subtree for a tree T. Okay. So here there are the vertices of subtree rooted at B. So if you choose B as a root vertex, so for a subtree, then which are all the vertices that subtree includes is B, C, G, H and I. Next, coming on with the 2 more terminologies, that is depth and the height. What is depth of a vertex and height of a tree? We define depth for a vertex and height for a tree. Depth of a vertex V is the length of simple path from root to V. Simple path length from root you take to that vertex, particular vertex V. So the depth of the vertex V is found out. The height of the tree is the length of the longest simple path from root to a leaf. So it is the longest simple path from root to a leaf, wherein leaf will not be having further child. Okay. So we'll have that in an example. Same tree here is illustrated to know the depth and the height of a tree. Depth of a vertex C. If you just take any vertex, you can take any vertex. Here if you take the depth of vertex C. What is the depth of a vertex in a tree? It is the simple path length taken from that root to that vertex. Okay. So the depth of vertex C of a tree in the figure is 2. They tell that though the depth of vertex C in this tree is what? 2. That is, we count the tree levels top down starting with 0 from the roots level. So we'll count what? The level of a tree. So C vertex is at which level? It exists at the level 2. So that will be the depth of that particular vertex C. Okay. So the level starts from the root, that is at level 0, then level 1, and then C is at level 2. So it will be the depth of vertex C. The height of the tree is, what is height of the tree? The longest path from root to a leaf. So the leaf of this tree are H, I, G and F. Longest is which one? H and I path. Okay. So height of the tree is 3 they tell. That is maximum level of its vertices. So maximum level is at what? 0, 1, 2 and 3. It is the 3 level. A to B is, from A is at level 0, B, D, E, S is at level 1, C, G, F is at level 2 and H and I is at level 3. So it will be the height of a tree, that is maximum level of its vertices. Then coming on with the discussion of another type of tree, that is binary tree. Binary tree is defined as an ordered tree. Ordered in the sense in which every vertex has no more than 2 children and each child is designated as either left child or a right child of its parents. And binary tree may also be empty. It is one of the property of a what? Tree. So binary tree, ordered tree, which will be having no more than 2 children and each child will be designated as left child or a right child. So binary tree may also be empty. It can exist with no vertices. It can have empty. It can be empty. An example of binary tree is shown in the figure below. Just the structure of a binary tree having a left right childs. Some will be having just one child, maybe right or maybe left. Okay. So the binary tree with its root at the left, binary tree with its root at the left or right child of the vertex is a binary tree, is called the left subtree or a right subtree. The tree which exists across the left child is called as left subtree. The tree which exists across the right will be termed as right subtree. Right child will form a right subtree and left child will be forming a left subtree. So in the figure below you can see some numbers are assigned to the vertices of the binary tree. The number assigned to each parental vertex is larger than all the numbers in its left subtree. So you can see the same binary tree here. So here they are given with some numbers. Again, what you have to understand while giving the numbers is the parental vertex is larger than the number given to the left subtree and smaller than that of a number given to the right subtree. Such tree are called as binary search tree. Now coming on with the discussion of sets and dictionaries. A set is a described, so set you all know. Set is described as unordered collection, possibly empty. There can also be an empty set of distinct items called elements of a set. A set is described as an unordered collection of distinct items. The elements can be very different. So that items may also be termed as elements of a set. A set is defined either by an explicit listing of its elements. You can directly have a set with the elements listed, or else you can specify its property. So for example, here there is a set defined with the values or an items or an elements as 2, 3, 5 and 7, or else you can define a set with its property also, that is S is equal to n of, wherein n is a prime number smaller than 10. So you can see the set all having the prime number smaller than 10. So some most important set operations what we already know in our previous knowledge. So sets are used for checking the membership of a given item in a given set, or else it is also used to find the union of two sets. So some operation like union is also performed on a set, and then you can find the intersection of two sets also. Okay, next, set can be represented in computer application in two ways. So first we'll consider the first way of representing the sets in a computer. First, consider only sets that are subsets of large set U. There is a large universal set U. You know that U is usually meant for representing the universal set. If set U has n elements, then any subset S of U is represented by a bit string of size n. S is a subset of U, then that S subset can be used for representing the bit string, so which is also called as bit vector. For example, if you have a universal set U is equal to 1, 2, 3, 4, 5, 6, 7, 8 and 9 elements, then S is a subset of that U, that is with the elements 2, 3, 5 and 7 can be represented by a bit vector or a bit string as 0, wherein instead of there is no existence of value 1 in the subset. So in place of 1 we have a bit value 0. 2, presence of 2 is there in a subset S, so we have that thing have with a value 1, represented with a value 1, and 3 is also there in the subset, so we have it with 1. 4 is not there, which was there in the universal set, but however in subset we don't have a value 4, so there we have the value 0, and 5 we have it as 1, and for again 6 it is 0, and again for 7 it is 1, and for 8 and 9 it is 0 and 0. Okay, so you can represent the tree or a set, sorry, it is not a tree, you can represent a set by a bit string, or else we can also call it as a bit vector. Second way is to represent the set in a form of a list, okay, which in list structure which indicates the set's element. You can have the list for representation of a set's elements. Two principal points of distinctions between sets and the list. If you just consider sets and the list, how it actually differs. First, a set cannot contain identical elements. You cannot have a same elements in a set. A list can have a repeated values. Secondly, a set is an unordered collection of items. Therefore, changing the order of its elements does not change the set. So if you go for changing the order of elements which is there in a set, so it will not have any effect. So it is an unordered collection of items, whereas a list is an ordered collection of items. List in the sense that in the list which one comes second, which item comes third, so it is all ordered exactly, so which is opposite to that of a set. Okay, in a list it is ordered collection of items, and in the set it is unordered collection of items. In computing, usually in a computing environment, the operations to perform for a set or multi-set are usually like searching for a given item, adding a new item, and deleting an item from a collection. So operations what we perform for a set or a multi-set are few, like searching, adding, deletion and all. Okay, so you can go for adding with a element into a set, delete, or you can go for searching for a particular element in a set. Next, one more terminology what we are supposed to discuss in this session is a dictionary. Dictionary is nothing but the data structures that actually helps to implement these operations related with the sets. It's a data structure which actually helps us to implement these above operations like addition, deletion and searching operations in a set. So the abstract collection of objects which play several operations are called as abstract data types. Okay, the abstract collection of objects with several operations that can be performed on it are called as abstract data type, or as ADT. The list, the stack, the queue, the priority queue and dictionaries are all important examples of abstract data types. So wherein there will be a formation of a collection of objects which will be used for performing some operations like addition, deletion, searching and all. You have certain special collection of objects requirement for performing certain operations. So all these data structures play a vital role in performing the operations, and it is a good examples of abstract data types. So these are the thing which we have supposed to go for having the things studied in the session 10, that is trees, again sets and the dictionaries. So the references for these contents what I delivered is given here in this slide. Then we are having some few multiple choice questions which we will be discussing. So the first one is, a tree or a free tree is connected dash graph. The tree is a connected dash graph. So it's a connected, again, whether it is an acyclic, cyclic, both acyclic and cyclic, or none of this. A tree is a connected acyclic graph. Okay, so the answer goes with acyclic. Secondly, a graph that has no cycles but not necessarily connected. There is a graph which may have no cycles. It is acyclic, but not necessarily connected. It may not be connected. So the graphs are not connected. Then it may not be termed as a tree, but it is termed as what? Is it a forest or a dense? It is termed as a forest. Then third one, the number of edges in a tree is. The number of edges in a tree is always what? 1 less than a number of vertices, equal to the number of vertices, 1 greater than the number of vertices, or none of these. So the number of edges in a tree is always 1 less than the number of vertices in a tree. So the option is A. Correct answer is A. Then fourth one, the rooted tree is usually depicted by placing its dash on the top. The rooted tree is always having what thing on its top? It's obviously the root, not the leaf nor the parent. Okay, it is the root which is at the top of a rooted tree. It is depicted with the root on the top. Then if UV is the edge of simple path from root vertex, then U is said to be the dash of vertex V. So if UV is a simple edge or a path from vertex, root vertex, then U is said to be what? Parent or child or sibling or none of this. U is said to be the parent of vertex V. Vertices that have same parent are said to be, so the vertices who are having same parent are said to be a leaf, descendants, siblings, or none of these. It is siblings. Next, the depth of a vertex V is the length of the simple path from dash to V. Depth. If we want to tell about the depth of a tree, so depth of a vertex V. So we define depth for a vertices. Okay. So depth of a vertex V is the length of the simple path from which vertex to that V is, from parent of its or root or leaf of its or none of this. So you have to see the depth of any vertex having the path from nor its parent nor its leaf, but it is root. Okay, from root, if you have a path followed towards that particular vertex, you will get with the depth of that vertex. Okay, a vertex with no children are called as what? So obviously it is what? Is it leaf or descendants or siblings or none of this? The vertex with no children is termed as leaf. Okay, the dash of a tree is the length of the longest simple path from root to the leaf. What actually gives us a longest path from root to leaf? From root to leaf, if we go on with the longest, that to longest path, okay, from root to the leaf, okay, so we will get with what thing of a tree? That is it getting you with the depth of a tree or a height of a tree or a path of a tree or none of this? It gives you what? It is the height of the tree what you get if you choose with the length of longest simple path from root to a leaf. At last, a set is described as dash collection. It can be also empty of distinct items called elements of a set. A set is a collection of items, distinct items is all okay, fine. Again we are having with one more property, is it an ordered, unordered, grouped or none of this? It is a unordered collection. It is an unordered collection, whereas list is a ordered collection of elements. Okay, so this will end up with the questions related with a multiple choice questions on this session. Sorry, two more are there anyhow. So a data structure that implements sets operation is called data structure that implements sets operation. Which data structures helps us to perform with the set operation, as I defined with the one of the term here in this session, that it is dictionaries. Dictionaries lets us with data structures which helps us to perform the operations related with set. Okay, it is dictionaries. And the last one is the dash is defined as an ordered tree in which every vertex has no more than 2 children and each child is designated as left or right child of its parent. Which is that ordered tree? Is it a binary tree, linked tree, parental tree or none of this? So it is a binary tree. So anyhow, these were all the multiple choice questions related with the slides which is presented to you related with session 10 of unit 1. So once again the questions, MCQ question numbers and the answers. So thank you.